So the big question that we're interested in is how do economic institutions and organizational practices shape the time path of individuals' opportunities and outcomes? And in particular, to what extent do they increase the persistent effects of luck by amplifying the impact of initial success on final outcomes? Now, there's evidence from a number of spheres of such amplification effects. Let me just mention two. In a fairly recent paper in the Journal of Financial Economics, Nanda et al. Examined performance persistence among venture capitalists. And after documenting the persistence of performance, they also used disaggregated data to find that the persistence of performance, the likelihood that early success is followed by later success, is actually enhanced by the fact that those VCs who achieve early successes are granted preferential access to deals after their early success. In a slightly different context, Zhang et al. In a paper in Science Advances documented that the disproportionate scientific productivity of elite researchers, those who've performed well in their early careers and have made it to elite research institutions, can be largely explained by the fact that these researchers are given substantial labor advantages, namely larger research groups, and that this is an important factor over and above any inherent differences in talent. So there's a common mechanism suggested by these two examples, namely advantages in the form of extra resources, as in the second case, extra training, extra mentoring, that are granted to early strong performance, increase the likelihood that their initial success translates into final economic advantage. And other examples of such a mechanism are fast tracks in firms and public agencies and academic tracking in schools. Now, one reason for granting such advantages to early strong performers, and henceforth we're going to call such advantages biases, is that they can improve the organization's selective efficiency. In other words, the assignment of productive resources and/or decision-making authority to the ablest individuals. In a paper that I wrote quite a while ago, I showed formally that using such advantages to favor early strong performers allows the organization to make more efficient use of ordinal performance information, or more generally, course performance information. But of course, at the same time, it increases persistence in outcomes beyond what would arise purely from differences in abilities and efforts. Now, if such advantages, if bias, were to be used even in settings where noise swamps underlying differences in abilities and efforts in determining performance, the persistence that we would see would be almost entirely the persistence of luck. And the first question that we're tackling in this paper is, could the use of bias to improve selective efficiency remain optimal even in such settings where noise swamps differences in abilities and efforts? And if so, why and to what extent? Understanding the drivers of the persistence of luck is important, since beliefs about luck as a determinant of success relative to talent and effort have been shown to influence attitudes towards redistribution. Okay, so to examine the effects of optimally chosen bias on the persistence of luck, we're going to analyze a two-agent, two-stage selection contest. In each stage, individual performance is the sum of time-invariant ability, privately chosen effort, and a transitory shock. After each stage, the organization is going to be restricted to observing only the ordinal performance ranking. And after stage 2, it has to make a decision which agent to select, and its objective is to select the more able agent. The agents in each period are going to choose efforts strategically to maximize their probability of being selected minus the sum of their per period effort costs. And importantly, after stage 1, the organization may, if it wishes, choose an additive bias to augment the stage 2 performance of the stage 1 winner. And in doing so, it's going to be maximizing selective efficiency, the probability of selecting the more able worker. Here are our main results. Firstly, we show that even as noise swamps heterogeneity in abilities in determining performance, optimal bias favoring the stage 1 winner is going to converge to a strictly positive level. It will continue to be optimal to artificially advantage the stage 1 winner, even as noise becomes arbitrarily important relative to the underlying differences in abilities. And hence, the persistence of luck is an inseparable consequence of maximizing selective efficiency. I'm just going to go back to see if I can get the slide. Yes, good, I can show the title. Secondly, we show that the persistence of early career luck is amplified by the ordinal nature of performance evaluation in a sense that we'll make very precise later on. And it's furthermore amplified by the strategic behavior of agents who have private information about their relative abilities. In the last part of the talk, I'm going to discuss a different form of luck and a different form of persistence. I'm going to talk about societal luck. When some agents have initial, although transitory advantages stemming from their identities, for example, their gender or their race, then we show that identity-dependent biases not only improve selective efficiency, but also reduce the persistence of this different type of luck, societal luck. And this finding regarding societal luck, reduced persistence, stems both directly from the organizational learning and indirectly from agents' strategic responses. Okay, so here's a quick outline. I'll say one or two things about related literature, then present the model in more detail, and then I'll focus on the analysis of the persistence of early luck. I'm going to break it into two stages. First, I'm going to consider the special case where agents have no private information about abilities in order to highlight the effects that arise even there. And then I'm going to consider the impact of introducing private information about relative abilities. In the first part, I'm going to actually draw a distinction between our results about the persistence of early career luck and our even stronger results about what we call the dominance of early career luck over later luck. And then finally, in the last part of the talk, I'm going to talk about societal luck. Okay, so very quickly, related literature. Over many years, there have been empirical studies of career paths within firms that show the importance of early performance for final success. There's a more recent literature exploring the implications of active organizational learning for the time paths of opportunities and outcomes. And our use of bias is active organizational learning. Formally, our model of organizational selection is one of a strategic interaction between strategic workers and the firm, and we combine a dynamic version of Lazier and Rosen's classic model of incentives and tournaments and my earlier pure learning model, which made no analysis of incentives. Okay, so here's the model. Two agents, we'll call them A and B, engage in two sequential rank order contests, after which the organization, who I'll call the firm, the principal, aims to select the more able agent. In each period, the performance of agent I is the sum of underlying ability, strategically chosen effort, and a random shock. The restriction to ordinal information is captured by assuming that only the sign of the performance difference, the difference between I's performance and J's performance in a given period, is observed. And I've put an asterisk because that's modified by the organization's ability to use bias, which I'll clarify in a second. So the performance difference is just the sum of the difference in abilities, the difference in efforts, and the difference in the random shocks. We will call the difference in the random shocks the noise. And we'll assume that the noise is IID across periods with a density G that's symmetric about 0, differentiable, and strictly log concave. After stage 1, the principal costlessly chooses a level of bias. If agent I won the first stage, in other words, if delta x1 was non-negative, then when the principal implements bias beta, the second stage contest, I will be declared the winner of the stage 2 contest if and only if the performance difference enhanced by the bias in favor of I is non-negative. Each agent chooses efforts privately in each stage to maximize the probability of being selected minus the sum of the effort costs over the 2 periods, where effort costs are quadratic. And we will model the underlying differences in abilities in the simplest way. We will assume that there are only 2 possibilities for the underlying differences in abilities. Either A is better than B by an amount H, or B is better than A by an amount H. And we will allow for the agents to be better informed than the principal ex ante about which of those 2 cases we're in. The agents assign a probability Q to A being better than B. The principal can't distinguish the agents, and so the principal will think of them simply as I and J. And again, I'm going to go back to stop the scrolling. Okay. Now, importantly, the parameter H, measuring the ability difference, can be interpreted slightly more broadly. It can be interpreted as the heterogeneity to noise ratio. Interpreting it that way allows me to suppress a scale parameter in the noise distribution. So the bigger is H, the more important is the underlying ability difference relative to the noise in the production process. As emphasized in the introduction, we're going to be studying the limit as H goes to 0 as noise swamps ability differences. And even though as H goes to 0, the selection problem becomes very difficult, it can still remain very consequential for the organization because I've not modeled the impact of ability on production after being selected. So if production after selection is very sensitive to ability, even in the limit as H is small, the selection problem can still be consequential. Okay, so just to be clear on the timeline, in the first stage, the agents observe who is likely to be better. They then exert efforts, the noise realizes, and the identity of the winner is observed. In the second stage, the principal chooses stage 2 bias. Seeing the bias, the agents exert second stage efforts. The noise realizes and the identity of the winner is observed, and the principal then selects the agent he believes is more able. It's helpful to observe that for any conjectured effort choices by the agent, when the principal chooses the second stage bias optimally, it's optimal for him to select the stage 2 winner. Okay, so let me now launch into the analysis of this model in the special case where agents have no private information about abilities. So that's the case where the parameter Q is a half, the 2 possible ability. It's equally likely that A is better than B or B is better than A, in either case by an amount H. In this case, for any anticipated stage 2 bias, the agents will choose identical efforts both in the first and the second stages. Consequently, in this special case, efforts have no impact on selective efficiency, hence no impact on the principal's optimal choice of bias or on the persistence in outcomes. Now, the fact that in stage 2, the agents choose identical efforts is a fairly well understood point from the Lazier and Rosen analysis of tournaments. Despite the asymmetries due to learning and bias, for the 2 agents in the second stage, the marginal benefit of effort is the same, because the value of winning is the same, the marginal impact of effort on performance is the same, and the pivotal realization of the period 2 noise is the same. As far as period 1 efforts, given the ex-ante symmetry of the agents, it's clear that there exists a pair of identical efforts that are best responses to each other. And we furthermore show that unequal efforts could not be best responses. So having derived this result about identical efforts in both periods, in this special case, we can therefore suppress the agent's efforts in the principal's problem of choosing bias to maximize selective efficiency. So the principal is choosing the bias to maximize S for selective efficiency, which in this simple case reduces to the probability of selecting the better agent. And that's the sum of 2 terms. The first term is the probability that the better agent wins the first period and then wins again in the second period, favored by bias, plus the probability that the worse agent wins in the first period, but the better agent wins in the second period, overcoming the bias that disadvantages him. Strict log concavity of the density of the noise guarantees the existence of a unique optimal bias, which favors the stage 1 winner, and which solves a very intuitive first-order condition. The first-order condition equates 2 likelihood ratios, one representing the informativeness of the first stage win. So think about I as winning the first stage. The left-hand side of this first-order condition measures how strong a signal it is about I being the better agent, that I won the first stage. And the right-hand side is also a likelihood ratio. Because bias is the choice variable, it is the informativeness of the first period loser achieving a draw in the second stage when disadvantaged by the bias beta. So both the left-hand side and the right-hand side are positive. The left-hand side is positive because winning the first period is obviously good news. The first-order condition must equate the right-hand side to that positive number. And if J achieves a draw in the second period against a bias, that will make the right-hand side positive. But the optimal level of bias exactly balances the informativeness, the strength of the good news about J from achieving a stage 2 draw against bias, from the informativeness, the good news about I from winning the first stage. Or put slightly differently, with bias set optimally, if the principal were hypothetically to observe a draw in the bias stage 2 contest, he would be indifferent whom to select. Consider the family of noise distributions with a shape parameter alpha, and density is given here. This is known as the family of exponential power distributions, or also as the generalized normal distribution. The family includes the normal, which is the case of alpha equals 2. As alpha goes to infinity, the density approaches uniform, and as alpha goes to 1, on the other hand, the density approaches the Laplace. So here's an example. Here's a picture showing you the different shapes of the density function as alpha varies. And here's a picture showing you the optimal bias, the bias that maximizes selective efficiency as the shape parameter alpha varies. Now, I want you to take away 2 things from this picture. The first is that the behavior of bias as the heterogeneity, the underlying difference in abilities varies, can be very varied. But the second thing I want you to take away is that as H goes to 0, the optimal bias remains strictly positive. And that's what I'm going to formally state and give you the explanation for on the next couple of slides. Okay.
Meg,
So,
I think you have a question.
Of course. Yep.
Yes.
Hi, Meg. Sorry, I have
Hi,
a quick
Helen.
question. I kind of missed it. How is the principal's utility actually defined?
The principal's utility The principal is interested in maximizing the probability of selecting the better agent.
I see. Okay. So I don't know if there is maybe time in the end. Maybe you could say something about an intuition where the principal cares about something like an ability plus effort or selecting. I mean, the term better can mean various things, right? So it
Okay.
can be
So,
some
so I
combination.
thank you, Helen. This is a very welcome question. I mean, selecting the agent whose underlying ability is higher. I'm not modeling the next stage, but I'm assuming that it's a production process which is more sensitive to ability than production in the current process that we're examining. So the principal would rather promote the agent with higher ability than lower ability. I'm also going to have something to say about what would or would not be different if the principal during this selection process were also concerned about the efforts the agents exert.
Yeah. Thank you.
Sure. Okay, so back to where I was. Ah, I don't know why it keeps scrolling, but I don't want it. Okay, good. So we're going to define the persistence of optimally biased selection as the probability that the stage one winner is ultimately selected when bias is set optimally. So that persistence is the sum of two terms. The first term is the probability that the better agent wins the first and then the second contest, advantaged by bias in the second, plus the probability that the worse agent wins the first and then wins the second, again, advantaged by bias in the second. And our focus is on what happens to this persistence measure as noise swamps heterogeneity as the parameter h goes to 0. And clearly it's important to know what happens to the optimal bias in this limit. And this is answered in the following proposition. As noise swamps heterogeneity, as h gets very small, the optimal bias continues to strictly favor the stage one winner. Even as h goes to 0, the limit of beta star of h is strictly positive. And consequently, the optimal learning strategy makes luck persistent in the sense that I've been using this phrase. The persistence in the limit as h goes to 0 when bias is set optimally is, despite the fact that as h goes to 0, performance differences are determined essentially only by luck, the persistence is nevertheless bigger than a half. So what I want to emphasize is the persistence of luck here does not stem from the organization using too much or the wrong kind of bias. It's a consequence of the organization pursuing the meritocratic objective of selecting the more able agent. Let me give you some intuition for this result. I've restated the first order condition determining the optimal bias here. Now, as noise becomes very important relative to the underlying heterogeneity and abilities, clearly the informativeness of both a stage one win by agent I, the likelihood, and the informativeness of a stage two draw against any bias beta, the right-hand side, both of those likelihood ratios approach 1. The informativeness vanishes as h goes to 0. So therefore, to find the optimal bias in the limit as h goes to 0, we have to find the bias which equates the rates at which the left-hand side and the right-hand side approach 1 as h goes to 0. Put slightly differently, the limiting bias as h goes to 0 is that value which maximizes not the level of selective efficiency, but the rate at which selective efficiency rises from a half as h rises from 0. Now, suppose that we contemplated setting 0 bias in the second stage and look at the first order condition. The right-hand side, the informativeness of a stage 2 draw, if bias is 0, is uninformative about the ability difference, no matter the size of the parameter H. While the left-hand side, the informativeness of a stage 1 win clearly rises with H. So the limiting value of optimal bias must be positive in order to equate the rates at which the two likelihood ratios in the first order condition rise from 1 as H rises from 0.
Meg, we have a quick question.
Good.
On commitment in the chat.
Yep.
So the question is there a commitment problem here? What happens if the principal committed to a bias before period 1 efforts? In that case, would the principal choose a different beta or not?
We've assumed that the principal is not committing, so he's responding optimally. There would in general be a difference between the commitment outcome and the no commitment outcome, because the principal, through committing to the bias, could strategically influence the effort decisions of the agent. Not in this special case where the agents are known to be, where the agents have no private information, but the commitment assumption could matter when I move to the more general case where the agents have private information. But the assumption under which we're working here is that the principal is not committing to the bias ex ante, but is responding optimally. Okay, but that's a distinction which doesn't matter until we introduce private information on the part of the agents. Okay, so I have a digression which I hope will partly answer some of what I think Helene was asking. I just want to talk briefly about the different objectives that the principal might have. We've focused on the principal as having the objective of maximizing selective efficiency, maximizing the probability of identifying the more talented agent. The stage 2 bias also affects the agent's effort incentives in each stage, though not the effort differences between the agents. One could ask, is there a trade-off between selective efficiency and agents' total effort incentives? And to ask this question, or what I'm going back to the most recent question, suppose the principal could commit to the bias. Would there be a trade-off between selective efficiency and the agent's total effort incentives? The answer is, in fact, no, in the limit that we're focusing on when noise swamps the heterogeneity. As noise swamps heterogeneity, the bias that maximizes selective efficiency also maximizes the agent's total efforts over the two stages. And to understand why, remember what I said on the previous slide, that the limiting bias, as H goes to 0, is that value which maximizes the rate at which selective efficiency rises with H as H rises from 0. We're working in a setting where performance is additive in ability and effort. So the derivative of effort and ability those two affect S in the same way. Or in other words, the rate at which selective efficiency rises with H is, for any H, proportional to the sum of agents' efforts over the two stages. To understand why this positive value of bias in the limit is optimal for a principal who wants to maximize aggregate effort, note that as H goes to 0, an increase in bias from 0 generates a first-order boost in stage 1 effort incentives, but only a second-order reduction in stage 2 effort. Okay, so I now want to go back to the main focus, which is the persistence of luck. And I want to derive a stronger result than the result I've derived so far. So far, I showed that optimal bias remains strictly positive, even as noise swamps heterogeneity and abilities, so that early luck is persistent. What I want to show now is that early luck, under very general conditions, when the principal optimally biases the two-stage selection contest, will dominate later luck. So the principal's a crucial assumption has been that the principal's information about agents' stage 1 performance is ordinal. He observes only which agent performs better. One reason why that may be is that stage one performance may have occurred outside the organization. So the principal was restricted as to the information about the stage one performance that he could get. I want now to consider a counterfactual where the principal could actually base selection on whether the sum of the performance differences over the two periods was positive or negative. This is what the principal would do if he had access to cardinal information on the performance differences in each period. And I want to point out that under this counterfactual, early luck would still be persistent. The limiting value of persistence, when the principal could base the decision on this criterion, whether the sum of the performance differences was positive or negative, would be the limiting value of the probability that the sign of the second period overall performance difference matched that of the first period. And a simple symmetry argument shows that that probability is 3/4. Now, in this counterfactual, there's a very precise sense in which early luck and later luck would be equally important, in the sense that in the limit as noise swamps heterogeneity, the probability that an agent was selected, conditional on having been lucky in the first period but unlucky in the second, would exactly equal the probability that he was selected conditional on having been unlucky in the first and lucky in the second. And that's because the performance differences are treated symmetrically. What I want to do now is to examine how ordinal information, and more generally coarse information, as opposed to this counterfactual with cardinal information, how does ordinal information affect the importance of early luck relative to later luck, as measured by this limiting ratio? So we will say that early luck dominates later luck under optimally biased selection if this ratio exceeds 1. I'm going to call the ratio D0 for dominance in the limit as h goes to 0. Graphically, D0 is bigger than 1 if the probability of the pink shaded area here exceeds that of the blue shaded area. So in the limit as h goes to 0, the performance differences are entirely determined by the noise terms. The pink shaded area represents the probability of early luck determining selection. Agent I wins the first period, loses the second, but is nevertheless selected because the amount by which he loses the second period is outweighed by the bias in his favor. Later luck is measured by the probability of the blue shaded area. Agent I loses the first period, wins the second period by enough to overcome the bias against him. And clearly, this ratio, D0, would be 0 if limiting bias were 0, and it increases with the limiting bias. And so the question we're asking here is, under optimally biased selection based on ordinal information, is the limiting bias big enough to ensure that the pink shaded area is more likely than the blue shaded area? And I will show you conditions under which the answer is yes, and that's a stronger result than simply showing that the limiting bias is positive. So let the distribution of noise, the G function, be normal or thinner tailed than normal, and I will just at the bottom of this slide be precise about what I mean. Under this condition is sufficient for the following result. Given only ordinal information about the first period performance difference, early luck dominates later luck when bias is set optimally. Or formally, the limiting value of this ratio exceeds 1. Furthermore, as we think about coarsening the information available to the organization, going from the cardinal case that I described on the previous slide to the case of ordinal information, the coarser the information about early performance difference, the greater the extent to which early luck dominates later luck under the optimally biased selection process. So, as I said, here's the formal version of the sufficient condition in this proposition. The formal condition is that the function L, defined in this way in terms of the underlying density of the noise, should be convex. This function L is linear for normal distributions, and L is convex for densities G that are more log concave, thinner tailed, than normal, in the sense that ln G is a concave transform of ln F. So that's the precise condition. Now, to get some insight into why this result holds, this early luck is more important than later luck. D0 is bigger than 1, if and only if limiting persistence under ordinal information exceeds persistence that would emerge under cardinal information. Now, if the density of the noise is normal or has thinner tails than normal, that's going to make the optimal bias under ordinal information equal to or greater than the average of the contingent bias that would effectively be used if the organization were using the selection criterion of the sign of the sum of its performance differences. Actually, there's another effect, which is why this condition is sufficient but not necessary. The coarser the information available to the organization, the less variable is the second period bias, and that per se is going to raise the expected persistence, since the distribution of the noise is unimodal, and hence G is concave. Okay, so that's what I wanted to say about the special case of the model, when agents have no private information about their abilities. And I showed the results on the persistence of early luck and the stronger result on the dominance of early luck over later luck. Let's now introduce private information on the part of the agents and show that this private information, or in particular agents' strategic response to it, actually amplifies the persistence and dominance results. So now there are going to be non-trivial effort differences. And effort and ability we can think of as the strategic and the non-strategic components of merit. So what we're asking here is when agents can condition their choice of the strategic component on information about the non-strategic component, on their private information about who's likely to be more able, what consequences does this have for optimal bias and the persistence of luck? So go back to the general formulation. We continue to assume that there are only two possible values for the difference in abilities, H and minus H, but now both agents assign a prior probability Q to agent A being more able than agent B. So we're interested in Q bigger than a half. Both of the agents believe A is more likely to be better. But from the principal's point of view, the agents are indistinguishable, although the principal does know the value of Q, just not which agent it belongs to. So just as we did for the special case with no private information, we begin by understanding how the agents will strategically choose their effort levels, anticipating bias, and then we study what is now a non-trivial equilibrium in the strategic interaction between the agents and the principal. So beginning with the agent's effort choices, for all Q bigger than a half, and for any anticipated second stage bias favoring the stage 1 winner, the agents will choose identical stage 2 efforts. But more interestingly, in stage 1, the better agent A, the one they think is more likely to be better, will work strictly harder than his rival. So on average, the effort differential between the agents will reinforce the heterogeneity in their abilities, making stage 1 more informative. And because this is going to be important for the result on persistence, I want to explain the second part of this lemma. The first part of the lemma follows from the same logic as we used earlier. The second part is more interesting. So agents' incentives in the first stage stem from two effects: the rewards to winning stage one, because if they win stage one, they'll be favored in the second stage and hence more likely to be selected. But they're also concerned about the implications of winning the first stage on the nature of the competition in the second stage. Now, this first source of incentives, the rewards to winning in stage one, stemming from the increase in being selected, it's easy to show because the selection is zero sum, that these are equal for the two agents. But now let's suppose that agent A, the better one, the one likely to be better, worked less hard than agent B in stage one. And now let's think about the two stage two continuations. The continuation if agent A wins stage one and the continuation if B wins stage one. If A wins in stage one, he's going to be favored in the second stage. But because he's already thought to be better than B, and because we're conjecturing that he worked less hard in stage one, in the second stage, the two agents are going to be pretty confident that agent A is better. And hence the bias second stage contest is going to be more unbalanced, and so is going to induce lower efforts, compared to the case where agent B won in stage one. The consequence of this is that agent A would have an effort cost incentive to win stage one, because his effort would be enhanced by the prospect of having to work less hard if he wins in stage one, whereas exactly the reverse for agent B. He'd have an effort cost disincentive. But that means that the overall reward for agent A from winning stage one would actually be greater than that for B, which contradicts our starting assumption that agent A works less hard. So the only equilibrium for any anticipated bias favoring the stage one winner in the game among the agents is that agent A, the one more likely to be better, works harder than agent B. So we're now in a position to look at the limiting value of equilibrium bias, taking into account the effort incentives that we just studied, in the limit as noise swamps heterogeneity. The limiting value of equilibrium bias in this limit as noise swamps heterogeneity is strictly positive and strictly increasing in Q, the precision of the agent's information. And the consequence of this is that as noise swamps heterogeneity, the persistence of the selection process in equilibrium is strictly increasing in Q. The more informed agents are about their relative abilities, the more their strategic effort choices amplify the persistence of early luck.
Meg, we have another question from the chat on the previous point.
Yep.
What if the two agents happened to have a common yet incorrect belief about which of them is better? Would the agent presumed to be better also work harder in stage one?
Yes. So Q could be strictly less than one. For any Q, sorry about this. For any Q, I'm sorry. For any Q bigger than a half, as long as agents have some information, even if it's noisy, the one that they presume to be better will work strictly harder than the other agent. So this result is not dependent on agents being correct in their belief. They share the belief, and the belief must with some probability be correct. Okay, and so the interesting comparative static in the limit as noise swamps heterogeneity is that this strategic incentive of the agents and the fact that the agent more likely to be better works harder than the other agent results in a larger value of the limiting bias, the more precise the agent's information, And consequently, the more precise the agent's information, the more their strategic effort choices amplify the persistence of early luck. And under the sufficient condition I presented earlier, the more their effort choices amplify the dominance of early luck over later luck. And I want to just give some explanation because this may initially seem paradoxical. In the limit as noise swamps heterogeneity, the stage 1 difference in efforts is going to vanish. However, the limiting value of equilibrium bias, and hence the limiting value of the persistence of early luck, nevertheless rise with the precision of the agent's information, because the rate at which the effort difference rises with ability, as the heterogeneity rises from 0, is increasing in Q. And furthermore, the better is the agent's information, the more likely that the effort difference reinforces the ability difference, so the larger the rate of increase of the stage 1 informativeness with H as H rises from 0. Okay, so I'm now approaching the final stage, final section of the talk, which is societal luck. So we've been focusing on early career luck, the luck determining who wins the first stage. We now want to focus on a different type of luck, and luck stemming from having the right identity, the right race or gender or socioeconomic status, etc. That might benefit an agent at the early stage of careers. In fact, even before the two-stage selection contest we've modeled so far. And we're interested in this because there's a recent literature that documents how institutions may cause such initial advantages or disadvantages to have cumulative effects. So we're going to model the socially advantaged agent as coming to this two-stage selection process with an exogenous, commonly known head start, which we'll call alpha as distinct from bias, beta. This head start alpha is uncorrelated with ability and will assume that it additively affects only the stage 1 performance. So it's something that makes one of the agents more likely to win the first stage, but doesn't intrinsically affect the later stage and is not intrinsically informative about the ability difference that the principal is trying to learn for the selection decision. We'll assume the principal's objective remains the maximization of selective efficiency, and we'll assume that performance evaluation remains ordinal. And furthermore, that despite the fact that this head start is understood and is commonly known, the principal cannot intervene in stage 1, because stage 1 you can think of as occurring outside the organization. We'll assume for simplicity that the agents have no private information, so we're going back to the special case of Q as a half, and let agent A be the socially advantaged one. And we will define the persistence of societal luck as the probability that the socially advantaged agent A is ultimately selected. Now, conceptually, societal luck differs from early career luck in that both the level of stage 2 bias and the stage 1 efforts could condition on societal luck, on which agent is advantaged and how big that advantage is. We're going to distinguish between two regimes for stage 2 bias. One we will call the identity-independent regime, where the bias in favor of the stage 1 winner is required to be independent of whether the stage 1 winner was the socially advantaged one or not. And the other regime, identity dependent, where the organization is allowed to choose the magnitude of the bias according to whether the stage 1 winner was the socially advantaged one or the socially disadvantaged one. Now, suppressing for the time being stage 1 efforts, it's very intuitive that optimal identity independent and optimal identity dependent biases are related in this way. If agent B, the socially disadvantaged one, wins in the first stage, that's a really strong signal about his relative ability. And so if biases can be identity dependent, the organization would set a bigger bias than if it were restricted to identity independent biases. Whereas if agent A, the socially advantaged one, won the first stage, that's a good signal, but it's weakened by the social advantage, alpha. And so the identity-dependent bias in favor of A is less than what would be set under identity independence. Or to put slightly differently, identity-dependent biases effectively penalize the advantaged agent, no matter whether he wins or loses. Because in both cases, the advantaged agent achieved his performance aided by this exogenous head start alpha. The question on which we want to focus is how does allowing the biases to depend on identity impact the persistence of societal luck, the probability that the socially advantaged agent is ultimately selected, given agents' strategic responses to the advantage and the bias regime. So again, we begin with a lemma that describes how agents' efforts differ according to whether they are the socially advantaged or disadvantaged. We can show that for both bias regimes, identity independent or identity dependent, in equilibrium, the advantaged agent exerts a lower stage 1 effort than the disadvantaged agent, but overall maintains a positive net advantage. In other words, for the advantaged agent, the fact that he's exerting smaller effort is outweighed by the positive head start alpha. The logic behind this result follows a similar logic to what I used in proving the lemma when we looked at the implications of private information on the part of agents about relative abilities. The result here is different, but the logic is similar in that the effort differences stem from the agent's anticipation of how the two different stage 1 outcomes, the advantaged agent winning or the other guy winning, will result in different stage 2 efforts. And we can now examine the implications of what we've learned about efforts for the persistence of societal luck, which is the outcome in which we're most interested in. So firstly, we can show that if the organization is constrained to set second period bias in a way that is independent of identity, then societal luck is always persistent. The probability that the socially advantaged agent is ultimately selected is always bigger than a half. And that has a very mechanical explanation. Given what I've told you about efforts, the fact that even with strategically chosen efforts, the socially advantaged agent has a positive net advantage in the first period, the socially advantaged agent is more likely to win the first period. Since the bias in the second period is the same, whoever wins the first period, the fact that the socially advantaged agent is more likely to win the first period translates into his being more likely to be selected. In contrast, when biases are allowed to be identity dependent, the persistence of societal luck may in fact be entirely eliminated. We have a very clean example of a noise distribution for which the persistence of societal luck is a half, or the probability of the advantaged agent selected is a half, no matter the size of the head start. And to get a general comparison, we need to make a few additional assumptions. We need to assume effort costs are large enough that we can ensure uniqueness of equilibrium under both bias regimes. And then we can say for small enough heterogeneity and small enough head start, allowing the stage 2 biases to be identity dependent reduces the persistence of societal luck. And furthermore, a stronger result reduces the difference in expected utility between the agents. So what I want to emphasize is that our finding that identity-dependent biases reduce the persistence of societal luck stems from two distinct channels. The first channel is what I've talked about already, namely that for any given positive net advantage, identity-dependent biases effectively penalize the advantaged agent, no matter the first stage outcome. So that penalization is going to reduce the persistence of the initial advantage. The second channel is the strategic channel. Identity-dependent biases induce the disadvantaged agent to partially compensate for his disadvantage with even larger effort relative to his rival. And that strategic response further reduces the persistence of societal luck under identity-dependent biases. Now, as far as the final point in the previous proposition, when it comes to the overall comparison of expected utility between the advantaged and the disadvantaged agent, we can show that for sufficiently small head start, the extra cost of greater relative effort for the disadvantaged agent is actually outweighed by the reduced persistence of societal luck, and hence the difference in expected utility between the advantaged and the disadvantaged agent narrows under identity-dependent biases. So the lesson from this analysis of societal luck is that a non-discrimination principle for selection within organizations, namely requiring the organization to set the bias, the advantage for the early stage winner, independently of the societal advantage, can actually backfire by propagating disadvantages stemming from the failure of society to establish equal initial opportunity. So what might seem like a good approach for the organization to not discriminating on the basis of prior circumstances, but only on the basis of prior achievement, can backfire by causing societal luck to be more persistent. Okay, so I'm on to my conclusion slide. Piketty has argued that the idea that success is purely a matter of individual merit is a myth, and that luck plays a much larger role than we often acknowledge. We've set out to examine this using one model which we specialize in a number of different ways, and our key contributions are threefold. Firstly, we showed that making early career luck persistent is consistent with the goal of assigning resources to the most talented individuals. And furthermore, that the persistence of early career luck is actually amplified when organizations are restricted to course, and in our extreme case, ordinal performance evaluation. And persistence of early career luck is also amplified by strategic behavior of agents who have private information about their relative abilities. We then shifted focus to look at the persistence of a different type of luck, societal luck, and showed that when some agents have initial but transitory advantages stemming from their identities, what we call societal advantages, then identity-dependent biases not only improve selective efficiency, but they also reduce the equilibrium persistence of societal luck. And thank you very much.